Hello everybody, my name is Benjamin Toppin, and today I'll be doing my project on materials of the future. As you can see, I'm by myself, and that is of my own fault and my negligence, but I will be doing my best to give you an entertaining presentation, so I hope you enjoy this and do learn something from it. Today, my main focus will be on carbon nanotubes and nanoparticles. I will also briefly go over current materials that are being used, and then explain how carbon nanotubes and nanoparticles will be changing the way we see the world as of today. I will first be going over some of the facts, development, and uses of carbon nanotubes, as well as graphene, since that does play a very important role. And then I would like to talk to you about nanoparticles and the ways they will be affecting the world in the days soon to come. In the coming days, nanomaterials such as these will be affecting every single aspect of our lives, if they haven't already, as they can be applied to most anything in any STEM major. Once again, thank you for your time, and I hope you enjoy. In this day and age, metals such as aluminum, titanium, and steel dominate the engineering industry. Steel especially because of its ability to be combined with other materials to enhance certain properties. For example, when steel is combined with chromium and other materials, it forms stainless steel, which is much more corrosion resistant and is used in a lot of household appliances. Titanium, though more expensive than steel and harder to produce, is stronger, lighter, and can be used to create alloys, which allows for widespread use in aircrafts, ships, and industrial buildings such as factories and others of the kind. Aluminum is lightweight, durable, and non-corrosive by nature, and is widely used as a heat conductor and in electronics such as CPUs and cell phones. Being the lightest of the three metals, it is also used in the automotive industry for weight reduction, and its high corrosion resistance also makes it widespread in a lot of household appliances, just like stainless steel. Its most noticeable and common form is as aluminum foil, where it makes great use of its heat resistance and corrosion resistance. These three metals form the background of our modern engineering disciplines, and have for quite some time now. However, as time's progressed, researchers and scientists have found new ways to create stronger materials on nearly the molecular level, giving rise to a new material that we will soon see dominating the modern world. Carbon nanotubes can vary greatly in size, ranging from as thin as 1 nanometer in diameter to as large as a few hundred. It can also be as many as a few millimeters in length. Similarly to how graphene works, carbon nanotubes are bound together with sp² bonds, which is a strong form of molecular interaction that occurs when 3 carbon atoms react with each other, forming covalent bonds, each at 120 degrees apart from each other. They are also especially susceptible to van der Waals forces, which are distance-dependent interactions between atoms. And since carbon nanotubes are so susceptible to these forces, they give us a wonderful opportunity for us to create stronger and lighter materials than the ones we have today. There are 3 main processes used when creating carbon nanotubes. These 3 forms are arc discharge, laser ablation of graphite, and chemical vapor deposition. In the first 2 processes, graphite is combusted electrically using a laser, and then the carbon nanotubes developing in the gases are separated. All 3 methods require metal as a catalyst. However, the chemical vapor discharge process shows the most promise in creating carbon nanotubes. Using this process, manufacturers of carbon nanotubes combine a metal catalyst with carbon-containing reaction gases to form carbon nanotubes directly on the catalysts inside a high-temperature furnace. Of these 3 methods, chemical vapor deposition is the easiest to control, the cheapest, and produces the most carbon nanotubes per successful attempt. There are 2 ways to perform chemical vapor deposition, one relying solely on the catalyst, and another using plasma as a support. Using plasma as an aid, manufacturers can use lower temperatures than if they were doing a purely catalytic process. Thanks to its ability to bond to nearly any material, carbon nanotubes have found uses in almost every single field of engineering and beyond. For mechanical engineering, carbon nanotubes can be used in composites to increase durability, reduce weight, and reduce wear. This makes it especially useful in aerospace engineering, where it could reduce the weight of future builds by 30% compared to what would be possible with modern materials. Chemical engineers could also make use of carbon nanotubes, using them as catalysts. Carbon nanotubes have the ability to attach to almost any chemical species, and also have the ability to form strong bonds with molecules, creating highly stable compounds. However, bonding in such a way changes the structure and property of carbon nanotubes. To overcome this problem, Researchers have been developing methods of chemical modification to these carbon nanotubes, resulting in mechanical bonding. These bonds are just as stable as covalent compounds, while at the same time not altering the non-covalent structure of the molecule. Bioengineers also get the chance to use these carbon nanotubes, as their latent abilities could increase mechanical strength, optical strength, and electrical conductivity, resulting in a higher chance in biocompatibility, enhanced material compatibility, and cellular responsiveness. However, there is the issue of toxicity, which is still being researched to this day, and has yet to receive a definitive answer. Next, I would like to talk about nanoparticles, which by definition are a particle of some kind with a dimension less than 100 nanometers. They were first theorized by Richard Feynman in 1959, but we wouldn't be able to visually confirm this until 1981, when scanning tunneling microscopes and the atomic force microscopes were invented. Just for reference, 1 nanometer is 1/1000th of a meter long, and there are 25.4 million nanometers in an inch. In other words, if 1 nanometer was the size of a marble, 1 meter would be as large as the diameter of the Earth. Nanoparticles have also been observed to have size-dependent properties. In other words, materials, especially metals, act differently on such a small scale. For example, even the smallest of magnetic poles in between two nanoparticles can cause them to be joined together permanently. Nanoparticles can be made out of pretty much any substance so long as its dimensions are small enough. As such, it is very common for them to form naturally. Some examples of this would be cooking, manufacturing, and transportation, which allows materials to break down and release nanoparticles into the air. Nanoparticles can also be made in laboratories using top-down or bottom-up methods. Top-down methods require you to break down materials until they're small enough to be classified as nanoparticles. This can be done using lasers, drills, presses, or anything else that can cause a material to break down into smaller and smaller pieces. Though simpler than the bottom-up approach, it does run into the issue of having imperfect surface structures, with nanoparticles coming out with structural defects or impurities on their surfaces. Examples of the top-down approach are electron beam lithography and atomic force manipulation. The bottom-up approach, however, requires scientists to create nanoparticles from the atomic level up. Though more complicated than the top-down approach, it does reduce waste and allows for manipulation of the nanoparticles, which results in perfection being a much easier thing to obtain through this method. Though many processes for the bottom-up approach are still under development, some that have already been developed are hydrothermal synthesis and the organometallic chemical route. Thanks to their diversity, nanoparticles have a large range of present and possible future applications available to them throughout all STEM backgrounds. For example, in a mechanical engineering background, nanoparticles could be used as an additive onto modern-day materials. For example, if used like a top coat on glass, it could be used as water and stain repellent, an anti-reflector, or self-cleaning. It could also be used as a resistant to ultraviolet and infrared light, or make the glass electrically conductive. It could also be used as a polymer composite, reducing weight in planes, trains, and automobiles. These composites have already been implemented in tennis rackets, baseball bats, and bike helmets. If sprayed on fabrics, it could be used as a wrinkle, stain, and bacterial deterrent, as well as being used in energy deflection and personal body armor. Electrical engineers have already been taking advantage of nanoparticles, creating a transistor only 14 nanometers in diameter in 2014. Nanoparticles could also be used to create flexible electronic devices such as phones or circuits. And magnetic random access memory computers would be able to reboot without the loss of any data or memory in the case of a system shutdown. Doctors would also be able to benefit from nanoparticles, using them to create tools that allow for faster, easier, and more accurate diagnostics of diseases. Researchers are also looking for ways to grow tissues so that patients don't have to wait on a compatible donor and instead can have new organs grown in a laboratory. Thank you for listening to my presentation. In short, I have found that carbon nanotubes, nanoparticles, and nanotechnology in general is definitely where the future is headed. With its wide range of possibilities, I have no doubt that we will be seeing nanotechnology affecting every single part of our daily lives in the near future. And as an aspiring mechanical engineer, I find this very exciting. Once again, thank you for listening to my presentation. I hope that you all found this as exciting as I did, and I will talk to you later. Thank you.